Allow me to begin with a question. If you took the sum of all networking code you'd ever seen and cross-referenced it, would that set be internally consistent? Would it use the same threading models, the same synchronization guarantees, or even the same types to model the things that it's working on? If your experience at all resembles mine, then the answer to that question is a resounding no. But it doesn't have to be this way. We can change it. So please hold your questions for the end while I take you on a guided tour of the networking TS. The networking TS is a technical specification for the ISO C++ standard, and we can hope it will make it into C++ 20. It is an adapted subset of Asio, which is in Boost as Boost Asio, and which has been the de facto standard for network programming, other than making raw operating system calls, for the past decade. Bringing this relationship full circle, since Boost 1.64.0, Boost Asio is now forward compatible with the networking TS. So if you like what you see here today, you can download the latest Boost and start using it immediately. More importantly, though, than this focus on just networking, is the fact that the networking TS and Boost Asio before it bring us a powerful conceptual model for thinking about and writing asynchronous I/O in C++. But if Boost Asio is 10 years old, surely knowledge of this model has dispersed throughout the C++ community. The best practices are well known and widely applied. Unfortunately, that's not the case. Most of the I/O code that I see, at least, is very rigid and not very testable. It's littered with direct references to types and calls out to global state and functionality. File descriptors, sockets, and calls to things like nanosleep abound. How do you test code like this? You need an actual network connection, and perhaps most perniciously, you need to actually wait for the passage of wall clock time. I don't know about you, but I'm not very highly motivated to run a unit test suite which includes multiple 5-second sleeps on every compile cycle. And if you're not prone to run a unit test suite, what good is it actually? Perhaps more importantly to some is the fact that this approach to writing networking code means that if the underlying transport changes, your code has to be rewritten or refactored. Changes that abstractly change nothing, like changing from a TCP socket to a TLS stream, require vast, sweeping code changes. Additionally, while the networking TS and Asio offer a powerful conceptual model and guarantees, few people are aware of them and choose to use them. Practically every week on the C++ subreddit, there's a new networking-related library released, boasting proudly that it uses Boost Asio. Use being the key word here. It's used as an implementation detail to save the authors from writing operating system glue code. None of its guarantees or practices are passed through. Instead, we're left with arbitrary choices about threading, synchronization, and even the asynchronous model that will be used. What asynchronous model does the networking TS use? The networking TS is a proactor, which means that all asynchronous work has a beginning, a middle, and a distinct end. Unlike the reactor, you don't get a continuous stream of callbacks. You start an operation, it proceeds, and then it finishes, exactly once. This has a nice parallel with the synchronous domain, which we all intuitively understand. In the synchronous domain, when we want to start an operation, say a read on a socket, we call a function to begin that operation. So too in the networking TS. We call something we call an initiating function, but at the end of the day, it's just a regular function. As I/O proceeds, a synchronous operation maintains control of the calling thread, and I/O proceeds in that thread. This is, in fact, a definitional element of a synchronous operation. If it doesn't do this, it's not synchronous. In the asynchronous world, in the Proactor, however, we diverge. The initiating function, as implied by the name, does nothing more than initiate the operation and then promptly return. The actual I/O proceeds in the background. When it comes to completion, synchronous operations have a nice symmetry. Because they maintained control of the thread, they didn't return from the function, they have a ready channel, for transmitting the generated values back to the caller. They simply return. In the asynchronous world, however, we gave this up because we returned from the initiating function and allowed I/O to proceed in the background. So we must use an alternative. We must take in a completion handler, a callable object which we invoke with parameters which represent the result of our operation. When thinking about the asynchronous world, I find sequence diagrams are very helpful. So let's look at some sequence diagrams now. On the left, you can see the synchronous world, where we have two actors, the initiator and the operation. Pay attention to the lifetimes, and notice that the lifetime of the initiator both comes before and proceeds until after the lifetime of the operation, because the operation maintains control of the calling thread. As we move over to the asynchronous domain, we acknowledge the decoupling of initiation and completion by adding another object to our sequence diagram, the completion handler. Note the disjoint lifetimes. The initiator is active only long enough to initiate the operation. The operation's lifetime then proceeds untethered from the lifetime of the initiator until it becomes time for the operation to complete, at which point the lifetime of the completion handler begins. Let's see if we can write some code. Let's try and implement your typical TCP heartbeat. A loop that goes on as long as the connection is active and sends some data and waits and sends some data and waits over and over and over again. We imagine there's going to be some asynchronous operations in there somewhere, and I mentioned that asynchronous operations complete via a completion handler, a callable object. So we need a callable object, which we call heartbeat. It includes some members, the timer it's going to wait on, the socket it's going to write to, a buffer of bytes, and the number of bytes it's actually going to write. We then give it two member functions, a null member function called initiate, which begins our asynchronous loop, and a binary member function called operator paren, which is the function call operator necessary for this thing to be a completion handler at all. Let's take a look inside. In our initiate function, we defer to another function. Following the common wisdom in the C++ community about raw loops, we choose not to write one. And we say, we're going to write this function async wait then write, which waits and then writes. We pass it the usual suspects, and then at the end, we move ourselves into it. What a curious construction. Very common in networking TS code. The only thing this initiate function serves to do is initiate the operation. And we want to be the completion handler of that operation. And our usefulness in this frame of reference has expired once we initiate the operation, so we move ourselves into it. When the operation is finished, we will be called. Our function call operator will be invoked, and we will be given two arguments, an error code which indicates whether or not the operation succeeded or failed, and the number of bytes we actually wrote. If there was an error, if that error code is truthy, then we simply wrap it in a system error and throw it. Problem solved. But if there was no error, since this is an asynchronous heartbeat loop, we want to move on to the next iteration of the loop. So we just call initiate, and it starts all over again. Now, C++ objects don't just spring into being and have one of their members invoked and all of their data members conveniently populated, so we need some code to actually get this set up. We have a buffer of bytes, which we're going to write repeatedly, and an I/O context, which, for now, you can just think of as something that helps you perform I/O. We create a socket and timer, which are going to use this I/O context to perform I/O, and then we do some things which I've elided to get that socket connected. Then we construct our heartbeat object and initiate it. The operation will detach from this thread and go off and run in the background, and we can continue doing all kinds of work. Fantastic. Asynchronous I/O. But wait a second. The entire meat of everything that we're doing is in a function called async wait then write. And we have absolutely no idea what's in that function. But we suspect that it waits and then writes. But that's two things, not one. What kind of function is this? And what kind of operation does it initiate? Well, it is a composed asynchronous operation. An operation, which is asynchronous, which is composed from one or more other asynchronous operations. This is the fundamental building block of high-quality networking TS code. Writing iteratively more and more complicated asynchronous operations, leveraging the asynchronous operations written before, until finally you've written your entire application. But there are certain patterns and practices which must be obeyed. First of all, if we're going to compose two asynchronous operations, we need two asynchronous operations to compose. So which two could those be? Well, we would hope that waiting is a fundamental asynchronous operation of a timer, and we would be correct. But what about writing? If you've ever written any socket code, you know that writing isn't very straightforward, because a write operation can complete and succeed, but not have written all the bytes. So we need a loop which does some pointer math and calls in a loop and checks a condition. And that kind of sounds like its own thing, doesn't it? Its own operation. This is where we get into building things as blocks. But the networking TS itself headed us off and actually ships that operation inside of itself. It calls it std net async write, and it will just loop until it's written all of the bytes or until it fails. Fantastic. We have two asynchronous operations. Let's try and compose them. Let's implement async wait, then write. We take two template parameters, a const buffer sequence, which for the time being, you can treat as an opaque handle to a buffer of bytes. For the most part, you can assume it's a value type and you just pass it around. The second is the completion handler, the actual callable type that we're going to invoke at the completion of this composed asynchronous operation. We take the parameters that you would expect, the timer, the socket, how long to wait, that handle to that buffer of bytes, and the completion handler. The first thing we do is we set the expiration of the timer, because this is called wait, then write, not write, then wait. Then we're faced with a problem. I told you earlier, when I was talking about the Proactor model, that asynchronous operations are initiated and complete exactly once. But we have two asynchronous operations, and only one completion handler. So what are we going to do after we wait? We need something to glue the wait into the write. We need what the networking TS calls an intermediate completion handler. We'll use a lambda. We capture all of the state that we need, and we take exactly one parameter, an error code, which indicates whether the wait succeeded or failed. If the wait failed, we simply go to the user's final completion handler and we pass them that error code indicating failure and the fact that we wrote no bytes. We didn't even get to that point. Notice the difference in error handling strategy. Previously, I checked the error code, and if it was truthy, I just threw an exception. And now I call the user's final completion handler. This corresponds to the boundary between library and application code. In application code, you have all of the context necessary to decide exactly how you should cope with an error. Do you retry or try something else? Do you throw an exception or do you abort? But inside this library, we only have the context to understand that we're supposed to wait and then write. We don't know anything about what we're supposed to do if we can't do either of those things. So we do the only thing that makes sense. We punt that decision to the user. Problem solved. Now, overwhelmingly, waiting on a timer actually succeeds. So if that's the case, we call std net async write, and we pass it the socket and the buffer of bytes and the user's final completion handler. Because once we've finished writing, our composed operation, which waits and then writes, will be complete. So invoking the user's final completion handler will be the right thing to do because the operation will be complete. Now, we haven't actually waited. We've just set up what we're going to do after we wait. So we call async wait on the timer, and we move this lambda into that operation. Then we just fall off the end of the initiating function, and we're done. Conspicuously, we haven't waited or written. We've just set up a chain of operations which will happen in the future, which will have the effect of waiting and then writing. This is a defining element of an initiating function. If it actually did anything, it would do more than initiate, and we couldn't call it an initiating function anymore. Let's look at the sequence diagram. The initiator's lifetime is very short indeed. It calls async wait on the timer and is then done. The timer proceeds as it waits and then posts to an executor. What could this possibly be? More on that in a moment. The executor invokes our intermediate completion handler, which in turn calls async write on the socket. Now, async write is a composed asynchronous operation, so there will be some number of calls to async write sum on the socket to get those bytes actually written. Then we're going to post to this executor again. and that executor will then call the function call operator of the user's final completion handler. And we're done. But this executor, which we know absolutely nothing about, seems fairly central to our sequence diagram. Indeed, it seems involved in absolutely everything except the initiation. And that's because executors are an answer to a question which was implicit in the formulation of a proactor. When I say I/O proceeds in the background, where is the background? Do we go out to a global thread pool like std async does, or have we learned that pretty much everything std async does is a mistake? Indeed, we have learned that everything std async does is a mistake, so the Executors TS brings us the concept of an executor. Like an allocator, an executor is a handle to something. In this case, to an execution context. An execution context uses execution resources, say a CPU, to run code using execution agents, say a thread. Now, there's an entire TS on executors, and that TS's name was not in the title of this talk, so let's just review the ways in which the networking TS integrates with the Executors TS and allows us to leverage their power. There are exactly 3 such ways. The networking TS defines 3 operations on executors. Each of them offers all of the guarantees of the preceding and adds something. When we dispatch a callable object in an executor, we ask that it be run in the execution context, and nothing more. Notably, if the person calling dispatch is already running in the execution context, the executor and execution context are free to scheme against you and just invoke that function right away, below you on the call stack, which may not be what you wanted. But you may not really be too serious about the fact that you didn't want it. You may just want to give a hint to the executor and the execution context. After all, in C++, we love our hints for efficiency, which is where defer comes in. When you defer, you make all the same requests you make with dispatch, but you ask the executor and execution context nicely that they not invoke that work below you on the call stack. If you're really, really serious about it, though, you can use post, which allows that callable object to be invoked below you on the stack. Never. It upgrades the request to a demand. Wonderful. We understand the asynchronous model of the networking TS. But if we think back to my example, I hard-coded dependencies against sockets and timers. And at the beginning of this talk, I pointed that out as a problem with the current state of networking code. So how can we possibly solve this problem? How can we break this dependency on sockets and timers and make our code testable and reusable? Well, we can just write an abstract base class with a bunch of virtual functions and use some type erasure and pay a massive runtime cost. That doesn't sound too interesting to me. Or we could go back to Bjarne's keynote yesterday and use concepts. We could take a step back and look at our operation and ask, what are we actually doing? Do I really care about the socketness of the socket? Well, no. We don't do anything to the socket that requires that it be a socket. We don't go and disable Nagel's algorithm or say, hey, what's your remote endpoint? Instead, we only care about a small number of operations that can be performed on it, which can be distilled to a concept, and which can then be mocked and can be substituted for things like a TLS stream. Fantastic. So what about the socket is it that I actually care about? Well, we write to it asynchronously. So we don't care that it's a socket. We care that it's a stream we can write to asynchronously. We could say that we don't actually want a socket, we want an async write stream. And fortunately, the networking TS provides this concept for us. It places requirements on everything that purports to be an async write stream. It says if you are an async write stream, you must have a null remember function getExecutor, which returns the executor associated with you. And you must have a binary member function, AsyncWriteSum, which takes a const buffer sequence and a completion handler and behaves kind of the way we expect a write operation to. The verbosity of this slide is a side effect of the fact that I shamelessly copy-pasted it from the networking TS itself, and therefore it's filled with standard ease. Now, while we're on the topic of testing, you can't test something if you don't have a mock, so let's write a mock async write stream. You can see it right there. It's called mock async write stream. We need an executor to return from that null remember function, so we store an executor. We don't really care what it is. We also need a buffer of bytes for us to write into, because the easiest way for us to test this is going to be copying down the bytes that are written to us and then examining them later to say whether we succeeded or failed. We then provide that null remember function getExecutor. It simply returns the nested executor. Fantastic. Then we declare the binary member function, AsyncWriteSum, which takes a const buffer sequence and a completion handler. Let's take a look inside. The first thing we do is we prepare two variables, because we're going to call our completion handler with exactly two values, an error code, whether we succeeded or failed, and the number of bytes we actually wrote. Then we interrogate the const buffer sequence, and if it contains bytes, we're going to try to write them. So we copy them into our buffer, and then we do some pointer arithmetic and fiddle with sizes and counts. If we didn't succeed in writing any bytes, that must mean that our buffer is empty, which means it's the end of file, so we report that error. Then we package up all these values we prepared, and we bind them along with the completion handler into an executor, and then we use post to submit it for execution. Just a few slides ago, I mentioned 3 operations on executors, and I said that each had at least the guarantees of the former. And now I've written some code for you, and I said, let's just use the most onerous of the 3, the one that has the most requirements. Why did I do this? In simple terms, because the networking TS said so. To flesh that out, I'm completing an asynchronous operation from inside the initiating function of that asynchronous operation, which means that if this was called in an asynchronous loop, exactly the kind of loop we wrote for a heartbeat, the operation would complete and invoke the completion handler, which would occur below it on the call stack, which would then initiate exactly the same operation again, which would then complete immediately and invoke the completion handler below it on the call stack. It doesn't take much imagination to figure out that this is a Stack Overflow waiting to happen. And we don't like undefined behavior around here, as Andre pointed out yesterday. So instead of dispatching in these cases, we'll just post. You can take solace in the fact that not many asynchronous operations complete inside their initiating function, since that kind of belies the point of being asynchronous. Armed with this mock, let's go and upgrade our initiating function so that it's testable. I've added 2 new template parameters. Unfortunately, I don't have C++20, so I'm using type name and naming my template parameter and hoping that someone looks at it and imagines that it models a concept. Or they can read the documentation or sift through compiler errors if they really want to. I've also changed the corresponding types in the parameter list to my initiating function. But take a look at the body of the function. It's exactly the same. This is a concrete expression of something I pointed out a few slides ago. We didn't care that we were using a system timer, and we didn't care that we were using a socket. We just didn't know that we didn't care yet. All we really cared about from the get-go was that we had a timer that we could wait on, and that we had a stream we could write to asynchronously. And so all we had to do was change some types in a parameter list and add 2 template arguments, and we were off to the races, except now we can use an infinite number of types instead of just 2. So let's write that much hyped unit test. We need a buffer of bytes for our mock to write to, and we need something to write. So let's pick the world's simplest HTTP request. Why you're sending that as a heartbeat, I don't really know. Now we declare another of these I/O contexts, and earlier I waved my hands and said, this is just a type you use to perform I/O. But now that you all know what an executor is and what an execution context is, I feel confident in revealing to you that this is also an execution context. And it has a very useful property. That property is that it doesn't do any work unless you explicitly surrender a thread to it, which gives you very tight control over when all those asynchronous parts execute, which will become important in just a moment. Now we create a mock waitable timer, whose implementation I leave up to you, the viewer, because it didn't fit very nicely on slides. So just imagine that it works. Then we create a mock async write stream, which we actually saw on a preceding slide. Next, we declare 3 variables to instrument the invocation of our mock completion handler. Then we begin our asynchronous operation. We pass our mocks into it and decide that, hey, let's wait for 1 second. And then we pass in a lambda as a completion handler, which simply writes down the fact that it was executed and copies out the arguments that were passed to it. Now I said an I/O context is an execution context which doesn't do any work unless you surrender threads to it. And we haven't surrendered any threads to it. Therefore, the operation shouldn't have completed, because if it has, that would mean that the initiating function was invoked, the completion handler was invoked from inside the initiating function, which is banned. So we assert that it didn't happen. We assert not I, because for I to be true, the completion handler would have had to run, and that's banned. Continuing, we now explicitly surrender our thread to the execution context. We use poll, which says, hey, if you have any work pending, you can run it right now, but I don't want to wait around, so if there's nothing, just return to me. We write down the number of handlers that were actually invoked. Now, we have a mock timer, but we didn't tell it that it could expire, which means that the async wait we initiate in the initiating function hasn't completed yet, which means its completion handler shouldn't have run, which means no handler should have been run, so we assert that that's the case. Then we go off and we tell the timer, hey, you can expire now. And then we prepare that execution context to run again. Then we surrender our thread to that execution context again, and we think about what's happening in the background. Since we told the timer it could expire, it's expired, which means it invoked the intermediate completion handler we defined on a previous slide. Which means that we've gone off and we've tried to write to our mock async write stream, and we know that writes on that type complete immediately. Which means that obviously some handler should have run, so we assert that. And our completion handler should have run, so we assert that. And we hope that it didn't fail, so we assert that. And then we do a complicated bunch of assertions to make sure the correct number of bytes were written and that the bytes that were written are actually correct. Notice how, at every step of the way, we had precise control over what was going on. The timer expired only when we allowed it to, and asynchronous work was executed only when we allowed it to be. There were no race conditions here. There was no hoping that 1 second is long enough for this assertion to fire, praying that the operating system scheduler doesn't conspire degenerately against you. No, we were in control. This unit test passes every single time. This is not an intellectual exercise. The first time I ever wrote a library using Boost Asio and the guarantees and practices that I'm talking about here, I received a bug from somewhere my application was deployed. I looked at the bug report and concluded there's a problematic ordering in which some of these handlers are being invoked. An ordering bug. That's enough to fill any developer with absolute terror. We're going to go into our unit test suite and we're going to write a loop, and it's going to loop a lot, and we're going to hope that the operating system scheduler messes up on one of those and we can see the bug. And then we're going to go and fix it. And how do we know when we've run that test enough to conclude the bug is gone? But I used the principles and practices of Boost Asio, now the networking TS. So I wrote a unit test, just like this. And it failed every single time. Then I went into the code and I fixed the bug. And that unit test is still part of the unit test suite, and it succeeds every single time. This is the gold standard for unit testing. The only question should be, wait, why do we allow any less? Now, we can write an asynchronous operation. We can make it testable. But I've just opened Pandora's box. I've just talked about ordering bugs. And when I hear something like that, my mind goes to data races, race conditions, thread safety. How does that possibly tie into the networking TS? How does the networking TS behave with parallelism? Well, to understand this, we have to break down what exactly we mean when we say concurrency and parallelism. In a technical sense, concurrency is taking an operation, splitting it up into parts, and not caring whether those parts are executed interleaved with the parts of other operations. Trivially, this is what we've been doing. We took async wait, then write, and we split it up into parts. And I don't really care if you go off and you read in between two of the parts of that operation. Bingo, it's concurrent. But what about parallelism? What about whether those parts can be invoked in parallel at actually the same time? What does the networking TS say about that? The networking TS is completely silent on the matter. The networking TS kicks that can down the road and says, parallelism is a property of the execution context. So if the execution context has 5 threads, then you might have some problems. And if it has 1, well, then we're all good. But if we think about the structure of an asynchronous operation, there's a relationship between the parts. Cause and effect are part of physics, not just computer programming. And therefore, we know that initiation has to happen before completion, which means that if we have one operation running, and it's the only thing that uses any of its arguments, it's definitionally thread safe. It's data race free. But what if there's more than one operation using the same socket? This is a fairly banal use case. Let's pose this as a question. Is this code thread safe? Let's say that I add a new object. Let's call it process. It looks like our heartbeat object. It has an initiate and it has a function call operator. It stores a socket, a buffer, and a number of bytes. Peering inside, we notice that when we initiate, we read from the socket into that buffer. And when the operation completes, we throw on error, and then we process those bytes, and then we initiate again. This is a typical read, process, read loop, which everyone who's ever written a server has seen before. It's not some exotic piece of code. So let's take a look here. Here's the code where we get things started. We've seen this before, except now rather than just kicking off a heartbeat loop on the socket, we kick off a process loop on the socket, which pretty much everyone who's ever written a network server is going to have seen before. But is this code thread safe? Is it data race free? Let's think about it. I call async read sum inside a member of the process object. And I call async write sum deep down inside a call to std net async write. I call it in an intermediate completion handler of an operation initiated by an intermediate completion handler. Now, if those two things can't happen at the same time, there's nothing problematic. Because sockets are thread compatible, not thread safe, we need to synchronize access to them. So if those two things can happen at the same time, we're in trouble. But if they can't happen at the same time, then we're not in trouble. So, for example, we can write code like this, where I reveal something below the fold. That is that we use this property of I/O contexts, that it only runs work in threads that are explicitly surrendered to it, and I only surrender one thread to it. It's a single-threaded program. It's data race free by definition. But what if I want to uncomment that line? What if I want not just to have one thread, but to have 2 threads? To do something inconceivable to the authors of Node? What could I do then? Well, I would need some way to customize the manner in which this code was executing. I'd need some way to inject my synchronization requirements, to inject intelligence about where and when and how certain things should be executed. I would need to customize the executor. I would need a way to associate an executor with my completion handler. And then, since problematic accesses can occur in intermediate completion handlers, I would need a way for that association to be honored at every level of the asynchronous operation I was passing that handler to. The networking TS provides this customization point for exactly this. If I know that I'm running in a multi-threaded environment and that I need to not run at the same time as some other handler, I can just provide an executor which gives that guarantee. Associate it with my completion handler, pass it in, and rest easy knowing that that operation obeys the requirements of the networking TS, which our operation currently doesn't. So we need to fix that. As I mentioned, this guarantee needs to be met at every level. Every intermediate completion handler needs to honor the executor association of the user's final completion handler, because your intermediate completion handlers are using objects that were passed to it at the initiation, so you can only use those when the user has told you it's safe to do so, and that's only when you're running in their associated executor. The way in which this class works is you pass in a completion handler as the first template argument, and then a fallback executor as the second, in case the user has not given an executor association for that type T. The type then provides you with a static member function and a type alias. The type alias, called type, is the type of the executor that you should use. And the static member function takes in a completion handler and takes in an executor and either returns the executor associated with that completion handler or just returns the fallback. Now, going through and specializing a class template for every intermediate completion handler sounds like a chore. And fortunately, the authors of the Networking TS understand that it sounds like a chore, so they gave us a shortcut. The unspecialized version of associated executor will go off and check the type T that's given to it. And if it has a nested type alias called executor type, then it assumes that that's the type associated with it and assumes that it can call nullery get executor on an instance of that type to get that executor. If that type isn't there, it just unconditionally returns the fallback executor. Armed with this knowledge, we're ready to upgrade our asynchronous operation. We need to move outside the world of lambdas, unfortunately, because we need to actually add special members to our object. It's no longer sufficient for it just to be callable, like all lambdas are. So we take in the usual suspects as template parameters and we store them, just like the lambda did when we captured. And we take and we give it a function call operator that is the result of copying and pasting the body of the lambda. Then we add two new members, the members necessary to maintain that guarantee I talked about, given the property of the unspecialized version of associated executor. We provide that nested type alias, executor type, and we go down and we use networking TS machinery to say, hey, can you give me the type of executor associated with this handler? And failing that, can you give me the type of executor associated with this waitable timer? Because this intermediate completion handler is a completion handler for an operation on the waitable timer, it makes sense to fall back to the waitable timer's associated executor. We then provide a nullery function, get executor, which uses some more networking TS machinery to say, hey, can you get me an actual instance of the associated executor given this completion handler, and just fall back to this executor if it doesn't actually specify an associated executor. Now we need to make some slight tweaks to our initiating function, namely we tear out the lambda and we construct an instance of this write-op class, and then we use that instead of the lambda. As a consolation prize, the code of this function became slightly shorter, although I think the previous slide more than makes up for that. But now we can make some slight tweaks to the example code we've been using, and we can get a program that's well behaved. We can take our heartbeat and process objects and make them templates, templated on an executor type, an instance of which they store and with which they associate, given the customization points I've told you about in the preceding slides. Then, moving on to the code that actually gets things running, we see something new. We see a strand, which is wrapped around an executor. What is a strand? A strand is a kind of executor. It's an executor which only allows one piece of work to run at a time, regardless of the execution context which underlies it. So if there's one thread, or 15, or 500, no matter how much work you submit to that strand, only one piece of work submitted to that strand will be running at any one time. In short, it ensures the kind of synchronization that we require. We associate our objects with an executor of this type, and we initiate both operations. Then we spin up a worker thread which submits itself to the execution context, and then we submit the main thread to the execution context. This transforms the execution context into a thread pool with two threads. But our operations are no longer associated directly with that execution context. Instead, they're associated with a strand. And the strand makes sure that only one operation at a time can be running. It doesn't matter what thread it's running on, so it's not exactly like a thread, but it makes sure that only one of them is running at any given time. Which raises the question, why do we have parallelism in this example at all if we're just throwing it away? Well, imagine that we have 1,000 clients. There's no reason that client A can't run on one thread and client B can't run on another thread, and then they swap back, and then client C gets involved. But it's very important that we don't have thread A running on one thread and client A running on another. This is what the Strand does. We have a Strand associated with each connection, and we can rest assured knowing that each connection appears to be single-threaded. Fantastic. We know how the networking TS behaves in the face of parallelism. And we know how we can kick the can down the road to our users and make them responsible for taking care of that. We also know how to make operations testable, and we understand the asynchronous model of the networking TS. But we're stuck passing around callable objects. And what if I don't feel like being in JavaScript-esque callback hell? What if I want to write some code that looks like this? Could the networking TS enable code like this, where I pass a special type as the completion handler to an asynchronous operation, and magically, somehow, I get back a future. And then I can allow the execution context to run and actually run the operation, and somehow the future is completed. The question, more broadly, is can I customize the completion mechanism used by asynchronous operations in the networking TS? The answer is a resounding yes. We can use the universal asynchronous model, which says that initiating functions, they don't take completion handlers anymore. They take completion tokens, which are some kind of token to some mechanism of completing the operation. Then we go off and we defer to a customization point called async result to obtain an actual completion handler and a return type. And then we proceed with that completion handler, and the rest is taken care of by whoever wrote the customization point. Let's take a look at that class, async result. It takes two template parameters. The first is the completion token type, and the second is a function call signature, like what you would see when you instantiate std function. Inside of itself, it has a type alias for the completion handler type. It has a type alias for the return type, and it's constructible given an L value of completion handler type. It has a null remember function called get, which returns the value you're supposed to actually return from the initiating function. This unspecialized version is suitable only for completion tokens, which happen to be completion handlers. So how would this look if we had useFutureT as completion token? Well, we would get a completion handler type which contained a promise, and which, when invoked, just fulfilled the promise. Our return type would be a future. The constructor, which accepts an L value of completion handler type, would extract a future from that promise and store it in an instance of this object. And then when we call get, rather than having no body and returning void, it would return that future. It would move it out. And indeed, this is exactly what happens for the specialization for useFutureT, which is provided by the networking TS. Now, let's go and integrate this into our initiating function. Notice how the final template parameter is no longer handler, now it's a token, which also changes the final argument type. And notice that I no longer return void, I just kick the can down the road and tell the compiler to figure out what I'm actually returning. Maybe it's void, maybe it's not. I declare a signature type. We know, throughout this entire talk, that we generate two values, an error code and a size t. So we have a function signature type, which is an error code and a size t. Then we actually instantiate the async result class template, given our token and the signature type that we just declared. Then from that, we extract the completion handler type. We're trying to get that completion handler so we don't have to change too much about how our operation is actually written. Given this handler type, we can construct it from a completion token. This is specified by the networking TS. Then we can use that completion handler to create an instance of our instantiation of async result. From here on through the next few lines, nothing really changes, because we've obtained the completion handler, an actual callable object which we can use to write normal asynchronous operations. The only thing we need to do is add a last line. We need to return r.get. Normally, that's going to be void, because overwhelmingly, people interact with these operations by passing around completion handlers. But sometimes it's going to be a future, and sometimes it may be something even more esoteric than that. The point of customization points is that you don't have to worry or think about it. It's taken care of by the machinery for you. Now you know everything you need to know to write a composed asynchronous operation in the networking TS. So let me leave you with the important takeaways. The first and most important one is don't write against concrete types. And don't make assumptions about types you don't need to. If you don't care about the socketness of something, don't assume its socketness by making it a socket. And if you don't care that something is a system timer, don't assume that it's a system timer. Don't use concrete types as a stand-in for an assumption that didn't need to be made. When you write initiating functions, make sure they're not recursive. No one likes to get a bug report from out in the field saying, hey, your program caused a stack overflow when I wrote the most usual asynchronous loop in the entire world. Remain agnostic in the face of parallelism. Threading is really, really hard. So don't think about it. Kick the can down the road and let your users deal with it. They'll thank you for it because they actually know more about their threading requirements than you do. And they're going to appreciate having to write one piece of threaded code which customizes your threading model rather than two, the one they actually want to write and the glue code because you assumed a bunch of things that aren't true about their application. So just assume you're always in a strand, whether it's actually a strand from a Strand executor or an implicit strand where everything just happens to work out, whether because it's single-threaded or there's no data races. Maintain and honor the executor association and everything will just work. Or if it doesn't, it's your client's bug and not yours. And those are my favorite kind of bugs. Resolve completion tokens to completion handlers so people can receive completion notification in the way that they choose, not the way you choose. They're going to come at you with futures and coroutines, and you don't want to go hacking that into your library. Instead, you want to say, hey, here's this nice customization point, just instantiate it for whatever type you want. Most importantly, never ever write one operation where two will do. Decompose every problem to the simplest problem and solve that. And then use the techniques I've talked about throughout this talk to compose them in a pyramidal manner. In this way, you'll never get into that dreaded situation where you begin a new project or a new part of an existing project and realize that what you desperately need is just a little bit of something you embedded inside a staggering, untestable monolith somewhere else. Instead, you want tiny, agile pieces, which have clearly defined and flexible rules which allow you to compose and reuse them, with types you haven't even thought of yet in threaded environments you couldn't possibly imagine. Are there any questions? On the left.
I feel like I have a lot of questions, but I come from a background of using Asio a good bit. One really small thing, the first, the slide where you had your, the unit testable code, were you calling poll?
Here.
Yeah, I was just curious, the first poll that you do, and no handlers get run because the timer wasn't expired yet. When you call the second poll, like the fifth line down, that would only run the intermediate handler, right? Because poll guarantees to run one. Wouldn't you need to run two polls to get the intermediate handler, the timer, and then the async write?
Well, there's poll and then there's poll one.
Oh,
and
okay.
poll run runs one and poll runs any that it can until it runs out of work.
Great. The other kind of more abstract question that I had is, since I'm used to the existing Asio, I don't understand executors very well. Is the context an executor, or is the context contains a default executor, or how does that relation?
So a context is, you can think about it in terms of arity. You have one execution context and you have an infinite number of executors, because executors are just a handle to that. On one of the slides here, you can see that the context is a context, and I call get executor on it to get a handle to it out of it. And those, because they're handles like allocators, they can't throw when you copy them and all that good stuff. But they all go back to one I/O context. Just like right now in Asio, there's one I/O service. It's just that in Asio, you can't change away from an I/O service, whereas in the networking TS, it's like, just use whatever executor you want.
Okay, thank you.
Hey, can you tell a bit about the current state of the networking TS as far as how close it is to actually make it to any standard, and
My understanding from talking to someone who goes to every single standards meeting is that the networking TS itself is fine, but they made the perhaps wise but not timely, I guess, decision of deciding that it needs to integrate with the Executors TS, and everyone is just running all over the place bike shedding the Executors TS. So the thing that's holding it up, I believe, if you look at the mailing list, is there's a paper that integrates the networking TS with the Executors TS, like it strikes a bunch of verbiage from it and just says, go look at the Executors TS. But the 3 operations that I posted on the slide for Executors, the networking TS actually maintains those and then redefines them in terms of stuff from the networking TS, which is why I chose to present those and not all the random member functions that the networking TS says Executors have.
Okay, I mean, my real question is, I want to use it. Do I have to use Boost, or is there some GCC experimental?
Well, the author of Boost Asio actually has a machine-translated version of Asio that's been completely renamespaced that you can find on GitHub, and it's what I used to test all of these slides. Right? I didn't just go through and rewrite them ad hoc to change the namespace. The other thing that you could do if you're really feeling adventurous is you could use Boost, but then just have a compatibility header that kind of like pulls the whole namespace into std.net, and then you just very carefully delete it when that stops working, but that's kind of undefined behavior because you opened std and it's not what you're supposed to do.
All right. All right. Thank you very much.
Thank you very much. On the left.
Oh, hi. Can you briefly talk about the relationship between this networking TS with coroutine?
So I don't know if the networking TS itself actually has it because I didn't check it out, but I know that Boost Asio has integration with Boost coroutines. Like you pass something called spawn, I believe it is, in, and then somehow something happens to convert it to coroutines. I don't use coroutines in my day-to-day job, so I don't barrel down too deep, but I have seen spawn, and I did read the documentation for it once, and I know that it has some interaction with Boost coroutines. Whether or not it actually has out-of-the-box integration with that coroutine, you can rest easy knowing that if it doesn't, you can just write your own tag type and write your own specialization of async result, and then it will magically work, which is the point of async result.
Okay, thank you.
Thanks.
Hi. Wanted to answer a couple of the questions you've been getting. I'm an author of the Executors paper. There's no TS. There's never been an Executors TS. It would be great if we had one, but we don't. It is moving very quickly, but it does not support a lot of things in your slides. And it's not looking like it will for 20, but yeah, we're working on it and appreciate your feedback. So thanks.
Thank you for that. On the right here.
Yeah, got another question. I think slide 32, maybe?
No, it's just back 3. This one?
Right. Yeah. Why do you need executor type? Can't you just check the return type of getExecutor?
Well, the real reason is because the customization point here says so.
Okay.
Like if you read the networking TS, it says there has to be a nested type alias, executor type, and then I make all these assumptions. I mean, on a conceptual level, you don't, because if we like want to zip back really far here in the slides here, you can see that this concept doesn't, which is one of the reasons why I have to use the like decal type hack, because there's no executor type inside an async write stream or a lot of the IO object concepts.
Okay. All right, cool.
Thank you.
When the coroutines will be accepted, maybe as a part of a language feature, we will have actually 3 ways to deal with the result of a synchronous operation: a callback, a future, and like coroutine stuff. So do you think we will eventually settle for one way, or will we have to support like every one of them?
Right. So in the slide where I talk about the universal asynchronous model, that's a name stolen from a paper that's very old. And it has a long preamble in it where it talks about all these competing completion notification mechanisms. And it shows a lot of very illustrative diagrams. And what it concludes is that if you look at all of them, there's a cost or a bunch of assumptions to them, except callbacks. Because you can implement all the other ones at 0 cost in terms of callbacks, but you can't implement callbacks in terms of all the other ones. It notably picks on promise and future a lot, because promise and future are very pernicious because they have almost a required allocation, and they have all sorts of synchronization inside of them, whereas when you use callbacks, you don't need that because of what I talked about with implicit strands. So I think what you're going to see is customization points that allow you to merge them, and then people are going to decide on them based on their application domain, what works for them.
Thank you.
Thanks.
Hello. I have used Boost SEO like before C++11, and I found out that the biggest pain with it was when I had some kind of operation, which probably like had two connections, and I passed stuff there and back and stuff, and with canceling.
Right. So
is it better now? I don't know, but
canceling is something that you have to handle in my experience, canceling is one of those things where you want to carefully structure the operations you're doing to kick the can down the road. So you want to say, okay, I'm going to wait and then write, right? And that's all that I do, right? And then at every layer of writing your application, you do that until you get to the highest level. Because at the highest level, you understand the cancellation logic. This is the kind of code that I write all the time. So at the highest level, you may know, okay, what's in play right now is a socket and 2 timers, right? And so maybe the completion handler for one of them is pending. But I need to maintain a data race-free program, so I know it's not executing right now because I'm sharing state with it. And I made sure that I have the right executor associated with me. Okay, so if the completion handler is pending, it's going to wake up, right? So I set a flag somewhere where it can wake up and be like, oh, I'm actually supposed to die. Okay, whatever.
So the canceling is still purely asynchronous?
But and if I call cancel, right, then they all complete immediately, right? And then I can just, go off and I know those completion handlers are going to come in. And yeah, it's all asynchronous, but what you do when you write an operation is you just don't care, right? Like that's the approach that you take whenever you write something in the networking TS. You shard it down to the very smallest unit of work, and you do just that, right? And then high-level concerns like, how do I cancel this? Or what kind of synchronization do I need? Or there's also a customization point for allocation. Like what kind of allocator do I want to use? All those decisions, just kick the can down the road on them because you don't have any idea how to make that decision, right? Like how should I allow for a wait then write to be canceled? Right? Should I give you some allocated handle that allows you to cancel the operation? That would require me to know that the types I'm operating on have a cancel function, which isn't part of the concepts that they're modeling, right? But at the highest level, I know when to cancel, and I know exactly which I/O objects might have completion handlers in flight. So in all the code I've ever written, I cancel or close them in the case of sockets right then and there. And the only time that's a problem with Asio is, I forget which version of Windows it is, where it's like you can cancel I/O, but it won't really cancel it unless you're canceling it from the same thread that you initiated it from. Something insane like that because of how I/O completion ports work.
Okay, thanks.
It's not a problem with Windows 10. I think the cutoff is like XP and 03. I'm not 100% sure whether it was that or Vista, but it stopped being a problem, and now we have like cancel I/O X, which just cancels all the pending I/O on a socket, and then you're good. Did I get all the questions? Excellent. I'll be around if anyone has any other questions. Thank you.